In this video, we are going to look at the rule of complements. So, rule of complements, where notice complement is spelled with an E as in the word complete. Because here we are looking at two sets or events that when combined complete the entire sample space. They form the entire sample space. So A and B are complements if A joined with B is the entire sample space. And A and B are mutually exclusive. This means that A and B have no elements or events in common, right? To be mutually exclusive, A and B can have no elements in common. So, for example, we can look back at rolling a fair die where we know the sample space consists of the numbers 1 through 6. Let's define A as the event of getting an even number, which in this case would be specifically 2, 4, or 6. And let's let event B be the event of an odd number, which in this case would be 1, 3, or 5. So here we see that when we join them together, we will get the entire sample space. So we write that as a union. A is a union with B, and union has its own symbol, which looks like sort of a U or a horseshoe. So we have A union B equals the sample space. So A and B are complements. Now, if A and B are complements so that their union is the entire sample space, then it follows that the sum of their probabilities, since it forms the entire sample space, must be 1. So what the rule of complement says is that we can find the probability of one of the events, say A, by computing 1 minus the probability of B. We see this in general as the probability of A equals 1 minus the probability of not A. And this is the rule of complements. For the example we are doing, we are going to look at the probability of at least 1. Well, let's be a little more specific here. At least 1, to make sure everyone understands, is the probability of 1 or more. So the complement of 1 or more is 0. So we find the probability of at least 1 by computing 1 minus the probability of none or 0. So the probability of at least 1 equals 1 minus the probability of 0, and this is what we're going to be using in applying the rule of complements to these sampling problems. Let's look at the sampling problem. What we have here are 60 items produced by a company that had a defective rate of 15%. They make a change in the manufacturing method and they're hoping that they have improved the manufacturing rate. But we're going to see what the probability is of when we randomly sample 5 items, we want to see what is the probability of at least one of the 5 items is defective. And we're going to be doing the sampling in 2 different ways. First, we will do the sampling with replacement. Then we will do the sampling without replacement. So remember, when we're sampling with replacement, what we have are independent events and constant probabilities. That means the probabilities are not changing. They will always be the same. So we want to find the probability of at least 1. So we are going to compute 1 minus the probability of none or 0. The probability of none, in this case, is the probability none are defective, which means the probability that all are good. So we need to know what the probability that they are all good is. So let's see here. We see that the probability of defective is 15% or 0.15. Since there are only 2 possible outcomes per item selected, either good or defective, the probability then of its complement, probability of good, has to be 1 minus the 0.15, which is 0.85. So even here we are using the rule of complements. So now let's compute the probability of 1 minus the probability of all good. So that is equals 1 minus the probability that the first one is good is 0.85, as well as the probability of the second, third, fourth, and fifth. So we have 0.85 multiplied by itself 5 times, or raised to the 5th power. So we get a probability that at least 1 is defective as 0.55629 when we are sampling with replacement. Now let's look at sampling without replacement. When we sample without replacement, we have dependent events and conditional probabilities. This means that the probabilities change each time we make a new selection because we are leaving out the previously selected items. We are still computing the probability of at least 1, which is 1 minus the probability of 0. So it's at least 1 defective, 0 defective, 1 minus the probability of all good. Since the probabilities are changing, we can't just use the 15% and 85% we computed earlier. We're actually going to need to know how many items are defective in the batch of 60. So that means we need to find what 15% of 60 is, and that's 9. So we have 9 defective items, and 60 minus 9 is 51 good items. We're now ready to compute the probability of at least 1. So let's see, we got equals 1 minus the probability the first item is good is this 51 out of the 60 total items. And then the probability the second one is good, since a good one has been removed, there are now 50 good items out of 59 remaining items. The probability the third one is good after leaving out 2 good ones, it's 49 good items out of 58 remaining items. And the probability the fourth one is good is 48 good items from the remaining 57 items. And finally, the probability the fifth item is good will be 47 good items out of the remaining 56 good items. and that gives us 0.56988. Notice that we have a higher probability of getting at least one defective item when we sample without replacement than we do with replacement, because we are removing the good items and getting fewer good items relative to the defective items left. So that is the rule of complements using examples of sampling with and without replacement. Thank you for watching this video.